In the skies of the 2030s, the era of classic dogfights and Top Gun heroics will be over. Pilots won't chase targets across open horizons. Instead, they'll command networks of stealth aircraft and drones moving faster than radar can follow. At the center of this future stands the F-47, America's sixth-generation stealth fighter and the flagship of the next-generation air dominance program. Each one costs roughly $300 million, yet only 2 official photos exist, feeding rumors about what's really taking shape inside Boeing's hangars. The stakes couldn't be higher. China's own 6th-gen prototypes, the J-36 and J-50, are already flying. So what makes the F-47 different? Can it justify its massive cost? And who will rule the skies of the 2030s? Let's find out. In 2025, Boeing was officially chosen to build the F-47 for the United States Air Force under next-generation air dominance. The award ended years of quiet competition and confirmed that Boeing, not Lockheed Martin or Northrop Grumman, would lead America's next stealth fighter effort. For the Air Force, it became the highest-cost aircraft start since the F-35. For Boeing, it marked a chance to reestablish its role in frontline combat aviation and to deliver the successor to the F-22 Raptor. Early planning points describe at least 185 aircraft. The projected unit price sits near $300 million per jet, around 3 times an F-35. Congressional lines for FY 2026 show about $3.5 billion tied to risk reduction, prototype refinement, and pre-production tooling. The program is built as a networked enterprise that includes sensors, electronic warfare, data links, advanced weapons, and collaborative combat aircraft that will fly alongside the manned jet. Public material remains extremely limited. Only 2 official images have been released, and both include warnings that the pictures may not match the final airframe. Boeing leaders have said first article work is in progress, and schedule updates in late 2025 moved the initial flight target to 2028. That timeline aligns with continued risk reduction funding and with the need to mature engines, sensors, and software in parallel. The low profile is deliberate. Keeping details out of view reduces the chance that competitors can mirror design choices while China pushes its own 6th-generation projects. Inside the Pentagon, the F-47 sits at the center of Air Force modernization plans for the 2030s. The goal is clear: extend reach well past current fighters, lower signatures across radar and infrared, and give the pilot the tools to manage a formation that includes autonomous wingmen. This contract sets the baseline for how the service intends to hold air superiority against a peer threat in the next decade. The Air Force has released very few technical details about the F-47, but the few that are public show how far this aircraft is meant to stretch beyond anything flying today. The stated combat radius is greater than 1,000 nautical miles, about a 25% increase over existing American fighters. That figure alone changes how missions are planned. Longer range means fewer refueling points, more flexibility in striking targets deep within contested areas, and less dependency on vulnerable tanker support. It's an advantage that matters most in the Pacific, where distance defines every potential scenario. Speed has been another headline feature. The F-47 is expected to reach Mach 2 or more and maintain supercruise, sustained supersonic flight without using afterburners. It's not just about top speed, it's about endurance at those speeds. Operating efficiently at supersonic levels means the jet can intercept faster, relocate without detection, and stay on mission longer without burning excess fuel. While exact figures remain classified, engineers hint that the aircraft's adaptive engines play a major role in balancing raw thrust and range. Stealth remains central to the design. Officials describe the F-47 as a broadband, low-observable platform, reducing both radar and infrared signatures. Instead of relying solely on shape-based stealth like earlier generations, it manages visibility across multiple parts of the electromagnetic spectrum. This kind of spectral management combines materials, coatings, and active electronic countermeasures, allowing the aircraft to adapt its signature depending on the threat environment. Inside the cockpit, the Air Force wants something closer to a command center than a traditional fighter layout. The pilot isn't just flying, they're managing a network of systems, including autonomous wingmen, data fusion, predictive displays, and AI-driven threat prioritization will let one person coordinate multiple assets in real time. One detail that sparked debate was the appearance of canard foreplanes in early concept art. Some experts think they're decoys added to mislead foreign analysts, while others believe they could be functional for agility and control. Boeing hasn't confirmed either theory. Finally, the F-47 is expected to evolve through block upgrades, meaning each production run could carry different sensors, coatings, or wing configurations as technology improves, making it a flexible platform designed to grow over time. The F-47 leans on a new class of engines that manage energy in a smarter way. Instead of running one fixed profile, an adaptive cycle can shift modes for cruise or for maximum push. On patrol, it sips fuel. Then it can swing to high thrust when the pilot needs speed or altitude fast. This is a big step for U.S. fighter engines since the F-135 era. The Air Force ties the design to next-generation air dominance propulsion work, with multiple engine teams like General Electric and Pratt, and Whitney building experimental X-series cores sized for 6th-gen loads. The brief is simple to say and hard to do: long reach, strong acceleration, and tight control of heat and noise that give a jet away. One headline aim is sustained supercruise. The F-22 proved the idea, but in a narrow band. Adaptive cycle flow paths widen that window. By routing air through different streams, the engine can trade efficiency for thrust or flip it the other way. That helps range, helps time on station, and keeps turbine temps lower, which matters for infrared visibility. Heat control is now as important as radar shaping. Modern sensors look for hotspots before they look for a radar return, so the package focuses on exhaust cooling, nozzle geometry that hides the bright parts, and coatings that spread heat across a wider area. Inlet design matters here too. If the intake keeps pressure steady and masks the fan face, the jet is harder to spot and the compressor runs happier. Power generation is the other pillar. The F-47 will feed hungry sensors, electronic attack gear, and onboard AI. That means larger generators, smarter power electronics, and a distribution system that can surge for short bursts without cooking the airframe. The risk sits in the mix, not one item. Thermal margins, electrical output, and stealth shaping have to live together without killing reliability. Too much heat and signatures spike. Too little electrical headroom and sensors brown out. The integration work now is about finding the balance that lets the pilot supercruise, manage a flight of wingmen, and stay hard to find, all on the same sortie. Think of the F-47 as a flying command node, not just a single jet. One pilot, supported by a set of autonomous wingmen, manages a layered fight that uses both crewed and uncrewed platforms. The immediate idea is simple. Send cheaper, expendable systems into the riskiest zones, keep the manned fighter out of direct fire, and use the pilot's focus to coordinate the whole package. Operational plans describe each F-47 paired with several loyal wingmen at a time. Those drones come in different sizes and roles. Small scouts fly ahead to map threats and hand back high-resolution data. Larger drone variants carry jamming packages or decoys meant to confuse enemy radars and surface-to-air networks. Then there are the heavy trucks, unmanned aircraft designed to carry extra weapons or fuel, letting the main jet push farther without landing. Scaling is ambitious. Pentagon planning documents and contractor briefings talk about building vast fleets of autonomous systems that operate alongside manned jets in the 2030s. Numbers cited in some planning circles reach 1,000 plus for certain classes of wingmen across the force. That scale turns the tactical equation on its head. Instead of matching one for one, a commander can saturate an area with drones, probe defenses from multiple vectors, and mass effects, where needed. Cost is a major factor. A single wingman can cost an order of magnitude less than a manned fighter to buy and operate. Even when you count development, logistics, and losses, the math favors using drones for risky missions. That lets commanders accept attrition that would be unacceptable for crewed platforms while still delivering persistent capability. Command and control is the hard part. A pilot cannot micromanage 10 separate drones at once. The model places an onboard artificial intelligence layer between the pilot and the swarm, taking high-level directives and translating them into tasks for each wingman. Secure, low-latency links move data and commands, while the AI ensures safe separation, target deconfliction, and mission timing. That arrangement raises tough questions about trust, rules of engagement, and resilience. What happens when links are degraded? How much autonomy do commanders allow before human oversight is lost? Defense planners are building layered fallbacks, local autonomy rules for drones, encrypted mesh networks to route around jamming, and mission-level controls that let the pilot retake authority instantly. Practical experiments are already underway. Simulations and flight tests show the concept can work at a modest scale. The next step is pushing those demonstrations into operational squadrons, ironing out doctrine, logistics, and legal frameworks. If those pieces fall into place, wingmen will change how air combat is planned and fought in the decades ahead. Funding a sixth-generation fighter means reshaping nearly every part of the defense budget. The F-47 and its fleet of autonomous wingmen sit at the top of that priority list, but the cost is measured in hundreds of billions spread across jets, drones, engines, sensors, and software over the next decade. To make that possible, other programs are already feeling pressure. Modernization plans for some legacy fighters are being trimmed, and upgrades to bomber fleets are moving slower than projected. The Air Force has made its schedule public in broad strokes. Manufacturing work for the F-47 started in 2025, with the first flight targeted for 2028. Funding lines for fiscal year 2026 highlight about $3.5 billion for ongoing risk reduction and production readiness. Those numbers only represent early spending, with total outlays expected to rise sharply once full-rate production begins. Every element of the program is expensive. The unit cost, around $300 million per aircraft, is nearly triple that of an F-35. That price tag reflects the complexity of the systems the F-47 must control: adaptive engines, networked sensors, and full integration with autonomous wingmen. The Pentagon's own budget documents describe the effort as a system of systems, meaning every component depends on the next. If one piece slips, the entire network does. The industrial base has to grow to meet those needs. Skilled labor, high-end materials, and classified manufacturing facilities are being concentrated at fewer locations to improve quality control. Boeing, the main contractor, has started consolidating advanced composite and avionics production lines, with subcontractors positioned around existing stealth programs. The move mirrors the supply structure once used for the F-22, where only a handful of cleared sites could handle critical components. All of this creates a balancing act for the Air Force. Each dollar directed toward the next-generation air dominance program is one not spent elsewhere. Congress faces constant trade-offs: fund the future fleet or maintain current readiness levels. The Air Force's bet is clear. It's banking on next-decade dominance, even if that means accepting short-term strain across other aircraft lines. The Navy's sixth-generation program, known as FAXX, runs on its own track but shares many ideas with the Air Force's next-generation air dominance effort. Both aim for stealth, range, and networked warfare, but the Navy's version must survive the unique limits of carrier operations. That means stronger landing gear, folding wings, and an airframe that can handle catapult launches and arrested recoveries. These are compromises the land-based F-47 never has to face, yet they shape every design choice the Navy makes. Boeing and Northrop Grumman have both shown carrier-based concepts that hint at what the FAXX could look like. Boeing's model resembles a tailless, diamond-shaped stealth jet, while Northrop's design leans closer to a blended flying wing. Each reflects the reality that space on a carrier deck is finite and maintenance cycles are intense. These aircraft have to pack long-range and large payloads into a smaller footprint, and they must do it while remaining compatible with existing carrier systems. Performance targets place the FAXX about 25% ahead of the F/A-18 Super Hornet in combat radius, giving it a reach of roughly 900 nautical miles. That extra range is vital for operating far from contested coastlines, where carrier groups might no longer be able to approach directly. Networking will be central to the concept. The new jet is expected to link seamlessly with carrier-launched drones and collaborative combat aircraft, sharing sensor feeds, targeting data, and electronic warfare control across the air wing. In the budget arena, the Navy continues to defend its independence from the Air Force program. Senate defense committees have reinforced the distinction, funding FAXX as a separate line item and rejecting proposals to merge it with next-generation air dominance. Navy leadership argues that sea control requires specialized aircraft and cannot depend on adaptations of land-based designs. The service's long-term goal is to have FAXX enter service in the mid-2030s, arriving alongside unmanned carrier assets and new deck infrastructure. Together, they're meant to keep the carrier strike group relevant in a world where long-range missiles and drones dominate the first line of every fight. China's push into sixth-generation development has accelerated faster than most analysts predicted. On December 26, 2024, two stealth prototypes were spotted taking flight within hours of each other. The first, a tailless Trije from Chengdu, was quickly labeled by observers as the J-36. The second, a cranked Delta twin-engine jet from Shenyang, earned the informal tag J-50. Both designs appeared to favor reduced radar signatures, advanced engine inlets, and internal weapons bays, signs that China is attempting to leap directly into the sixth-generation race alongside the United States. By early 2025, more sightings of the J-36 began circulating online. Satellite photos and commercial flight trackers captured multiple test runs, indicating that full-scale flight testing was well underway. While official confirmation never came from Beijing, state-affiliated outlets began releasing carefully staged footage of hangars and research facilities, showing partial glimpses of airframes consistent with the observed prototypes. China's 2025 military parade brought its drone ambitions to center stage. Several stealth drones were rolled out, including one shaped for loyal wingman operations. These designs mirrored aspects of Western projects, low observable profiles, internal bays, and apparent autonomous teaming capabilities. The message was clear. China intends to pair its next-generation manned fighters with advanced drones, creating an integrated strike and surveillance network similar to the U.S. Collaborative Combat Aircraft program. One of the most interesting developments is the twin-seat version of the J-20. Analysts believe this variant could act as a command node, controlling loyal wingman drones during missions. That approach would shorten China's development timeline by adapting an existing platform rather than waiting for entirely new aircraft. Still, large gaps remain. China releases almost no official specifications, and most assessments rely on open-source imagery, radio tracking, and speculation. The secrecy makes it difficult to measure progress, but the visible pace of testing suggests China is intent on challenging the U.S. sixth-generation lead far sooner than expected. Europe and Japan are moving forward on their own sixth-generation fighters, working in parallel but with shared priorities. The Global Combat Air Program, known as GCAP, brings together the United Kingdom, Italy, and Japan. The project aims for a mid-2030s entry and carries a multi-billion-dollar budget. Early design goals focus on adaptive engines, open software architecture, and the ability to team with drones, much like the American Collaborative Combat Aircraft concept. The first demonstrator is expected to fly before 2030, with Japan's Mitsubishi Heavy Industries and the UK's BAE Systems leading key sections of development. France, Germany, and Spain are developing a separate sixth-generation project called the Future Combat Air System. Its central aircraft, the new generation fighter, is set for prototype testing in the late 2020s and potential service in the late 2030s. Program value already exceeds 100 billion euros. Both initiatives emphasize digital design tools, rapid prototyping, and AI-supported mission systems to reduce costs and shorten timelines. Across both efforts, the trend is clear. These nations plan to stay relevant in the next era of air combat through collaboration, modular design, and shared drone control networks. The F-47 program moved from selection to first article work in 2025, with a first flight targeted in 2028 and a planning buy hovering around 185 aircraft. Officials have repeated performance numbers in public, including a combat radius above 1,000 nautical miles, top speed listed as Mach 2+, and sustained supercruise without afterburner. Those figures set high expectations, and they also raise obvious questions about engines, cooling, and fuel load. What we do not know is almost as important as what has been announced. Exact sensor packages, the detailed electronic warfare suite, internal weapons bay dimensions, and the control standards for collaborative combat aircraft remain classified. Renderings and a couple of official images offer hints, but final shaping and signature trade-offs could change as testing proceeds. Past demonstrators are acknowledged as inputs to the design, though their test data and lessons largely sit behind restricted walls. The program faces familiar risks, including cost growth, adaptive engine maturation, complex software integration, supply chain depth, and the challenge of fielding manned fighters and large numbers of autonomous wingmen at the same time. If those items align, the program can proceed on schedule. If not, delays or reductions in planned buy quantities become likely. The race for sixth-generation air power is no longer theoretical. The F-47's success will depend on how well Boeing and the U.S. Air Force can manage cost, risk, and timing, while China and Europe close in with their own designs. The next decade will decide who dominates the skies. Subscribe for more aviation deep dives.